Lesson 1.4. Before I start on lesson 1.4, before I even hit this bell ringer, I want to break down and give what I will call, in a sense, easier problems, in that I'm just going to make my own problems here, but at the same time, more difficult problems, because I can do things by hand a lot easier than I can by figuring out what the equations are, to really teach you limits. So what I want to work on here for a second is limits. I'm going to make this simple in the sense that I'm going to have a 3x3 coordinate grid here. Okay, so coordinate grid 3x3. I want to practice some limits. And so if you remember what a limit is basically it's an estimate of where the function is approaching. It doesn't have to be a real value. It doesn't have to be a real value. It's an estimate. So that means that places where the graph is undefined, we can estimate what it would be. We can estimate where it's going, even if it doesn't actually get to that value. Like we can estimate an infinity value, though that's not a real number. So this is just an estimate. And what I'm going to do here is I'm going to come up with just some random graphs. That's going to go straight up. Okay, and so this is my first extra example. You might be looking at your packet going, I don't see this. Well, of course you don't, because I just drew it. This is just me random. For the rest of this random examples I'm going to do, these are going to count by 1. So assume this to be 1, 2, 3, 1, 2, 3, -1, -2, -3, -1, -2, -3. This is obviously our y-axis, which, by the way, is equivalent. Let me do the equivalent symbol to f of x. And so the y value is what we're going to put there. This is the x-axis. So the x-axis value is what I'm going to put there. All right. So I want to make sure we understand how limits work. Here's what I ask you to do. This is not going in the grade book. So what I'm going to do is a bunch of countdowns, 5, 4, 3, 2, 1. And I want you just to guess the answer you think it is. And this classroom has 30 students. I am not going to know if you in particular are right or wrong. And if all 30 of us are doing this, you won't know who's right and who's wrong anyway. So here's what I'm going to ask you to do. Just speak vocally, because I realize that if you speak vocally, you will be more engaged in it and you will learn this quicker. I promise you, I've done this now. Y'all are the 4th class I've done this lesson with. Those, so yesterday, first period and third period in particular were very loud. And I felt like walking out. They knew their stuff. Second period was very quiet. And I walked out going, I don't know if they're going to limits any better than they did before. So I want to ask you to really engage here, speak up. And I promise if you do that, you will get this a lot better. The first limit I want you to estimate is this. I want you to estimate this limit. And what you'd have to do in the homework is you'd have a fill in the blank on Alex right here. The part I have written right here, this LIM f of x equals x arrow infinity, that would be given to you. Your job would be to fill in what this one value is right there. One more little reminder before I do my countdown is this is either going to be a numerical value, like 1, 2, 3, 0, or it's going to be an infinity or a negative infinity. Every answer, each graph is either going to go up to positive infinity, down to negative infinity, or it'll get flat with a constant y value, or it'll stop at a point with the constant y value. So that's your only options. So it's either goes up to positive infinity, down to negative infinity, or if it gets flat, it'll be flat on a constant y value or approaching the constant y value, or it'll stop at just a point that is a y value. All right, for this infinity, this limit when x approaches infinity, what is the answer for y? 5, 4, 3, 2, 1. 2. 1. I heard some voices. Some are correct, some were incorrect, and I don't know who was and who wasn't. But the correct answer is 2. Why is the correct answer 2? You're looking when x approaches infinity. That means x is heading off the graph in which direction? To the right. Infinity means it's not stopping. It's just continuing on. You're looking for the one piece that's going forever to the right, which is this graph right here. What's the y value? If it's constant or flat, if it's flat, that means the y value is not changing. What y value was it on? 2. It was going to the right forever, staying on the value 2. So 2 is the correct answer. All right, next one. I'm going to change this and this piece. This time I want to do -1 with a minus symbol after, where the power would go. -1 with a little minus symbol right there. 5, 4, 3, 2, 1. Okay, I hear 3 people. I think I only heard 3 unique voices. So we have 30 of us. I'm going to hear the majority. It doesn't matter if you're right or wrong. You take a guess. And by the way, I'll tell you, out of the 2 voices, I heard a positive infinity and a negative infinity. One of the 2 is correct. So I want you to take your best guess. 5, 4, 3, 2, 1. It's positive infinity. If you're wondering why, this tells you X, you're looking at -1. So there's 2 pieces that are approaching -1. That minus means the piece that's on the left of -1. This piece over here is on the left side of -1. So you're focusing on this portion, but you're focusing not on this portion of the arrow, you're focusing on this side, the one that's getting closer to the -1. What is the graph doing as we get closer to -1 on this particular C graph over here? I'll call it C graph. It's going up to positive infinity. That would be the answer. Yes, sir. Okay, if it was this piece, this is a great question. Because you knew it was this C graph is what you're saying, but you're wondering why was it not this arrow? If it were this arrow, X is not approaching -1. On this arrow, what's the X value that this arrow is approaching?
0.
Nope, that's the Y value. Negative infinity. So if you're talking about this portion right there, the way the limit would look is it's going left to negative infinity on the x-axis. Like an arrow means go left forever, but it's getting flat. And so with a limit, this is where it comes in. The limit's not always a real number. You're predicting what it's getting closer to. This arrow is getting closer and closer to the y-axis. It's getting flat. And so the answer for the y would be 0. That would represent this portion. Got it? This is a great question. I bet you a lot of people learned from that. All right, let's try another one. I'll do one small adjustment from what I just did. What if it had a -1 with a plus? 5, 4, 3, 2, 1. Starting to hear the right answers more in detail. Negative infinity. The answer is because you're looking at -1. So here's -1. What's the plus mean? The piece that's on the right. Now, you might be thinking, well, there's 3 pieces. Does this piece ever get near or approach -1? No, so you're ignoring this piece. So it's between these 2. That means the piece that's on the right, which is this one. Now, beyond this piece, you're looking at the side that's getting closest to -1, which is right here. It's going down to negative infinity. All right, I think I only have 2 more limits. So let's do 1 plus. 1 plus 5, 4, 3, 2, and 1. No, I only heard positive infinities. Did anybody else suggest something different? Was that a yes or get your hair out of your face? So positive infinity is not the right answer. Anybody else want to take a guess at it? 2. 2 is the correct answer. Why is 2 the correct answer? It doesn't matter if it's closed or open on limits. On a limit, the closed dot and open dot honestly make 0 difference. Make no difference. The reason why is this says look at 1. Here's 1 on the x-axis. So you're looking at 1. There's these 2 pieces. What does the plus mean? The one that's on the right. So we're looking at this piece that's on the right. Now at 1, you're looking on the left end, not the arrow. You're looking on the left end because that's the arrow, or that's the piece that's approaching 1 is right here. What's its y value? 2. That's why the answer is 2. Okay, and let me bring back every limit. There's 1 of 4 options. It's either going up forever, like we had here, down forever, like we had here. It's getting flat, like this one over here, or it's coming to a point. It's coming to a point, and so you just put the y value that's at the point. All right, last one for this example, and I'll have to make a new example. I want you to try this one. 1 negative. 5, 4, 3, 2, 1. I hear it over here. I hear two voices saying it. Its answer is 0. Okay. Okay. Okay, that's why we're doing this, so you learn. You're looking at the x value 1. So here's 1 on the x-axis. So there's 2 pieces. What does the minus mean? The left. Okay, now this doesn't mean continue on the left. It just means the piece that's on the left. So you're looking at this piece. Now, on this graph, every graph has 2 ends. Like there's the left end and the right end of this particular piece of graph. On this one, now I'm not talking about the negative as in the left side of the left piece. What I'm talking about is the piece that's getting closest to 1, which is this open circle. This open circle is where we are at 1. That open circle has a y value attached to it. I know technically it would be undefined, but like I said a second ago, with limits, open circles and closed circles don't matter. So what is the y value where that open circle is located? 0. And so that would be the answer there. Oh, great question. Are we looking for the x or the y? The y is f of x. Where you're filling in is what the f of x equals. This is telling you what the x is approaching.
Also, x arrow means that the
X arrow, great. Yes, I'm loving these questions because it's helping fill in missing information. The x arrow is telling you what x is approaching. Now, the reason they do x arrow is x doesn't actually have to equal the value. Earlier, I had an infinity. Technically, no x will ever equal infinity, but this is just saying as the x's get closer to infinity. Same concept here when I had the 1 minus. Technically, this graph never equals 1 on this portion, but as we get closer to 1, that means what is the graph as you get closer and closer to it? What y value is it going to? And the answer is 0. Okay, with that, I'm going to erase and give you a brand new graph so we can do this again. I think we might have answered some good questions there, and let's try our luck the second time. All right, so let me do. And honestly, I would have no idea what would make this equation. But that's the beautiful thing about drawing something at random. I don't have to know the equation. I'm just drawing the graph, how I want the graph to look to test your knowledge. Is it still 1, 2, 3? Yes, still counting by ones all the way around. Let's keep that simple. All right, first question I have for you. -2, negative. Remember, all this is what's given to you. What you would fill in on Alex, that kind of starting to look like a bracket, is you would be filling in this portion right here. There'd be a fill in the blank, and you would write your value right there. So I'm going to put that as a box, like as in that's my answer. You would not be writing this part. This part would be given to you. I think you get to, until you get to calculus, you don't actually have to write this portion by hand. That's always given to you. You're just filling in this portion. All right, so this one gave you a little bit of time to look at it. 5, 4, 3, 2, 1. The answer is 1. Okay, so what x value are we looking at?
Oh, I keep on looking at x.
X you're looking at is -2 right here. There's 2 pieces. Which one are we paying attention to? The piece on the left or the piece on the right? Piece on the left. Okay, but now you're only focusing in on -2. It's that open circle. What's the y value at that open circle? 1. Okay. I'm going to keep going random order. X approaching positive infinity. 5, 4, 3, 2, 1. 0. A whole lot of right answers. 0. As the graph goes, positive infinity means the graph's going forever to the right. You're finding the one piece that goes forever right. That piece, I tried to draw flat. I know I didn't do a good job, but I tried to draw it flat. What's the y value it's getting flat with? 0. So that would be the answer, 0. Okay, let me switch this up and make this negative infinity this time. What if this were x approaching negative infinity? 5, 4, 3, 2, 1. Positive infinity. Okay, this is saying you're looking at the piece that's going left forever. Out of these 3 pieces of graph, 1, 2, 3. Which piece goes left forever? 1, the first piece. So you're looking at the portion that's moving further and further left, which is this arrow. As we move further and further left, we're also moving further and further up. And that's why it was a positive infinity. All right, let's try. I don't remember all the ones we've done, so let me try this one. How about 1 plus? Five, 4, 3, 2, 1.
Negative infinity.
Negative infinity. Way to go, Jay.
Because it doesn't touch 3.
Okay, why is it, Jay? Because I didn't hear very many right answers that time. Jay, I did hear yours. Why is it negative infinity?
It doesn't touch 3.
Okay, start with the x. We're looking on the right side. So you look at 1 and you're paying attention. Most people said 3. If 3 were going to be the right answer, what would I need to do different here? It would be 1 minus. If it were 1 minus, the answer would be 3. So I'll change it in a second. But this says 1 plus, which means you're paying attention to this piece that's on the right side of 1. As we get closer to 1, what's this graph doing? Going down. Now, what's tricky is you see plus, and a lot of times we think of positives being up high. And I think that's why people said 3. So now let me give you the answer that would be 3. If the answer was 3 here, and you're talking about this piece, you would need to have 1 minus, which just means the piece that's on the left side of 1. And we're not talking about this one because that does not ever get to the x value 1. We'd then be talking about this piece. 1 on the left is approaching 3. Okay, I think I have 2 or maybe just 1 that I haven't done yet. How about this one? Negative 2 plus. Negative 2 plus. 5, 4, 3, 2, 1. 3. Okay, so you might not be there yet, but I have an actual bell ringer where we're supposed to do this. So I wanted to give you just some of my crazy examples I could draw. So now that when we look at the real examples, we might be able to do it together. All right, are we cool with that? All right, so now let's go to the bell ringer. Yes, bell ringer. Okay, number 1. Oh, before you get started, something very, I think, helpful. Maybe it's helpful. If you go to your Power School Learning, since this equation was so long, I've already programmed it in for you. If you don't want to have to type in that equation yourself to Desmos, if you go to lesson 1.4, which would be chapter 1 folder. Sorry, it's taking me forever. Got to log in, got to click pre-calculus. Okay, if you go to your chapter 1 folder and then go to the 4th lesson, you will notice that there are two Desmos links. So I'm scrolling down until I find 1.4. There's 2 Desmos links. Here we go, 1.4. There's a bell ringer on Desmos icon, and there's a Desmos pre-programmed graphs. I would suggest you click on the bell ringer on Desmos this time, and that'll directly open up some of these graphs for you. And the first one I've zoomed in to the right window so you can really see what's happening well. Now, my bell ringers I give you are not multiple choice. I know that if you are back in 1.4 and you open up, so I'm back to the Power School Learning 1.4, I'm going to open up the exam here, the exam 1.4. Come on in. Grab a packet and sign in if you don't mind. That'd be great. If you open up 1.4, I understand that these are multiple choice, but on my packet, they're not. I get that, but these should be multiple choice here. So since there's no multiple choice, what I'm going to give you is the part that would be given to you. Every single problem would have this lim f of x equals with an x arrow. All of them would have this and a negative infinity. And each answer choice would also have a limit of f of x. I'm going to read it properly this time. Limit of f of x as x approaches positive infinity. That's what the arrow means, approaches. So every answer choice has this. What changes is the value that after the f of x. And what does f of x refer to as by letter? The y. So you're trying to find the y here. Okay, first problem back over on Desmos. Here's our picture. Let's do this limit here. So basically the question you're asking yourself, and here's how you can kind of read a limit, is what happens to y as x approaches negative infinity? And now, since negative infinity is not a part of our directional, I'll say it this way. What happens to the y's as x goes off the screen to the left?
It's going up.
Okay, perfect. You can find a seat anywhere you want. Okay, oh yeah, y'all are answering it for me. Sorry, I was thinking about that. It does, it goes up as we go for off the screen to the left. So we're looking at out of these four ends of the graph. This one graph has what I would call four ends to it, or it would have four arrows. We're looking at this particular end of the graph right here. As we go left forever, this is the only piece that goes left forever. It's also increasing. So the answer would be positive infinity here. As we go left, the graph goes up. Okay, now let's talk about this piece. This is saying what happens to y as x, and instead of saying it approaches infinity, I'm going to say what happens to y as x goes off the graph moving to the right. So I'm going to do a countdown. I want everybody to get a chance to look at the graph. What happens to the y's as x goes off the graph towards the right? 5, 4, 3, 2, and 1. Negative infinity. Why negative infinity? Because it goes down. So that would be a negative infinity as your solution. And that so that's your solution to number 1. Yes, sir.
The top part is going to positive infinity too, right? So,
Are you talking about this piece?
yeah.
Okay, so if you're going to write a limit on this piece, what I'm going to do here is I'm going to click my graph. The limit, remember, a limit doesn't have to actually equal the numbers. You're writing really what the numbers are going to. The x value, if you notice, it's going to, if I zoomed out a little bit further, what you'll notice about the x values is they start to change slower and slower. They're approaching a number. They're going to get to a number. What number do you think these x values, so remember it goes x comma y. What do you think the x is getting closer and closer to?
1,
Nope. It says 6.7, 6.8.
7.
It's getting to 7. And if you wanted to check it, you could look on this side. This is 7.3, 7.2, 7.1. What number are these starting to, what x value are those centering on? 7. Okay. The y values, if you notice, never seem to center on a number. They just keep getting increasingly larger because they're going to infinity. This would be, yes, you're right, an infinite discontinuity. Very good. So if you were going to write a limit on the center of the graph, those on those ends, what would happen? So these are the end behavior, by the way. This is the end behavior. That is our answer. I'm now doing extra. If you wanted to write the other limits, so those are the end behaviors. This would be the left end behavior. I'm just going to say B. And this is going to be the right end behavior, right? Whoops, dash, end B for behavior. That would be your end behaviors there. If you wanted to write a limit on these two portions, you would have LIM f of x equals with an x arrow. They're centering on the x value of 7. So they would both have a 7. The difference is one would have a 7 with a plus. That would be this one on the right. And one would have a 7 with a minus. And so what's happening? Here's 7. The piece that's on the left, which direction is it moving? Up. And so your answer would be a positive infinity. And this says the piece that's on the right. On the right, what's happening to the graph as we approach 7 is going to negative infinity. Remember, a limit, the graph doesn't have to actually even be defined at all. It's just what's it heading towards. It's like a prediction in that regard. So these are extra. This is what I will call bonus. You didn't even have to pay me for that. I just gave that away for free. Okay, that was a bad joke. Won't tell that one again. All right, number 2. So on Desmos, here's what you can do. To make my picture bigger, I hid the equations. I'm going to open them back up. What you can do is just X out bell ringer number 1. We're done with that. So I'm going to X out bell ringer number 1, and then I'm going to click bell ringer number 2. There's something else I'm going to do. I zoomed way out, so I'm going to hit this home button over on the top right. So if you're following along on this Desmos, I would recommend you do the same so you can see the picture. This asks if the graph is continuous at 4. That means at 4, the graph is one piece. If it's continuous. If it's not, that means it's broken, discontinuous. What type of discontinuity is it? So I'm going to do a countdown. I'll let you look first. So you're looking at x a value of 4. at 4, is this graph consistently one piece going across 4, or is it broken apart? 5, 4, 3, 2, 1. Discontinuous or broken. Discontinuous or broken. Now, if it's broken, what type of break is it? Meaning, if you were to do your limits, let me explain it differently. I gave you, you're good. I gave you last class some pictures, and I said, hey, if the break is like this, it's infinite. If the break is like this, it's jump. You're right. Y'all are good. And if the break looks like this, that's what we call removable. Now I'm going to say it a little different. Now that we know our limits a little better, I'll say it like this. If the limits are going to infinity at the break, it's infinite. So if you were going to write your limits and you'd have to use a positive or negative infinity, it's a infinite break. If you were going to write your limits and they would be real numbers, but different real numbers, meaning this one's like a 2 and this one's a 4, if the numbers would be different, it's a jump. If you were going to write your limits for the two sides or the two pieces and they would have the same number, that's removable. So in terms of limits, the limit on the left would equal the limit on the right. This one and this one, they would not equal each other. One would be, these would be going to infinities. All right, having said that, look back at the picture at 4. So I'm going to click Desmos just because if I have the technology, why not? As I get closer and closer to the x value of 4, where are my y values heading off to? Negative infinity. What about on this side? Positive infinity. So if they're going to infinities, guess what our answer is? Infinite. This would be an infinite discontinuity. Technically, here's how you'd write that. You'd say infinite discontinuity at x equals 4. Infinite discontinuity at x equals 4. All right, and I'm going to do, don't want to write these limits just for extra practice? Okay, I hear no. One person has spoken. All right, number 3. Okay, so back on your graph. Open it up. If you're following along, just X out number 2. It's gone. We're on to number 3. So click that circle. And there's the graph. This, by the way, is what we call a piecewise graph. We call it a piecewise because if you notice the graph, though it looks like it's connected, it's definitely two different shapes. I have a parabola for most of the graph until over here. It's almost like the parabola has a broken arm and the arm goes off to the side here. That is called piecewise because it's putting together a parabola and a linear graph. On this one, does it appear to be continuous or discontinuous at x equals 2? What do you think? At x equals 2, here's x equals 2. Does this appear continuous or discontinuous?
Discontinuous.
So that would mean we'd have a gap. Let's zoom in and see. As I zoom in, actually, you know what? I'm going to use Desmos. If I have the tools, why not? I'm going to get to 2 and see if it's a closed dot or open dot. It's kind of jumpy a little. Okay, there it is. It says, mine says 2, 8 with a closed dot. This would be continuous. This graph would be continuous. Yes, sir.
What is like discontinuous? Say defined.
If it's discontinuous, the graph is undefined, except for that's not the with jump. There's one thing that could make it defined still. Let me show you. With a jump discontinuity, it could still say defined. So let me, so you see how that is a jump discontinuity? You see how that's a jump discontinuity? Technically though, with jump, what's a little bit weird is at the value of 2, you could still have a closed point, which means at 2, it's still defined there. But the top, which should be an open circle, which I don't think Desmos will put the open circle. Yeah, it won't on a piecewise graph. So technically on this one at 2, it's still defined, but it is discontinuous. Jump is the only one that can do that. So if it was removable, it would be undefined. If it was infinite, it'd be undefined. Jump, it could technically be defined, but yeah. Back to the original problem. This was continuous and defined as well. Okay, now notice I'm going to close off bell ringer number 3. I'm going to close that off. We're done with the bell ringer. There is a folder extra examples of the bell ringer, and so I wanted to show you a couple weird things. So here's number 1. I need to zoom out. You know what? We did the limits on this. What I do want to show you. No, I'm not going to do those. We did some extra examples, and I think my extra examples were better. So I'm just going to close out extra examples, and we're going to move on, unless anyone has a complaint about that. Okay, let's take a look now at example 1. So today, what are we doing? The majority of the lesson is going to be on what we call Extrema, which deals with maximums and minimums. I don't know if in your packet, if this slide was able to make, it looks like I ran out of space. So Extrema, that word Extrema, if you see Extrema, like anywhere on your packet, that word Extrema means maximums and minimums. Maximums and minimums. It's the extreme values of the graph. That's why they call them Extrema. So it could be a maximum or a minimum. Doesn't matter which. If it's either one, it's an Extrema. Maximum would be highest points of an area. Minimum will be the lowest points of an area on a graph. You could have more than one maximum. You could have more than one minimum. We will finish the lesson with average rates of change. That's just kind of like finding the slope when the graph is curving. So we're used to slope on a straight line, how much the rise over run, but on a curve, what do we do? And we'll get to that. But before we do Extrema, there's one example that just needs to walk through what we call increasing or decreasing or a constant function. Now, this is different from limits. Okay, separate your mind for limits. When you talk about increasing, decreasing, constant, you always are moving from the left to the right. Whereas I know when I just did those limits, sometimes I'd say, hey, if we're x approaching negative infinity, we need to look at the piece that moves left. We're not going to move left here. When we use the words increasing, decreasing, or constant, they're always talking like you read a book. As you read a book from left to right, is this graph moving up or is it moving down as you go from the left to the right? So this would be called an increasing function here. This would be a decreasing function. And this has a constant in the middle. What's tricky is on this side. What's happening on this side? Would you call this increasing or decreasing? Very good. A lot of people are thrown off because of that arrow going upwards, but we're looking left to right. This part is decreasing, as well as this portion is also decreasing. The constant is right there in the middle. That portion is what we would call the constant slope, or the constant part of the function. It's just in between x1 and x2 there, right in the middle. All right, so I want to get that out in the front end. In case you're making a note, I'll wait just a second. We will get to extremas on example 2, but first, example 1 here. Looking at this graph, it says use the graph of this function to state whether it's the intervals on which it's increasing, decreasing, or constant. With this word intervals, intervals are always x values, never y's. So I want you to note intervals are x values. So it's kind of like your domain, x values, but with parentheses only. So you don't have to worry about the brackets or parentheses. You just always use parentheses when we talk about increasing, decreasing intervals or constant intervals. So it's x values, but with parentheses always. Okay, with that, we're looking at this graph. Does this graph always increase, always decrease? Is it always constant, or is it a combination of some? Combination. What's the left half doing?
It's decreasing.
Decreasing. What's the right half doing?
Increasing.
Okay, let me tell you how students are going to mess up. They're going to look at this point, and I'm going to write it as a point so you can see where I'm getting the numbers. That point is in the middle of the graph, which means the x value is 0, and it's down 4 units. Inevitably, what happens is students will write it's decreasing, and they will say it's decreasing from like -4 to infinity, or they might even say negative infinity to -4. But that's wrong because we're supposed to go off the x values. Okay, so it's decreasing from wow, the F's got me there. It's decreasing from forever left to 0. What represents forever left? Negative infinity. So you're saying it's coming from the left, forever to the left, all the way to the value 0, decreasing. That's how you would write that. On the opposite side of the graph, we are increasing. So you're always moving left to right. The point at which we start to increase, the x value, is 0. So you would say you would start to increase from 0 going forever to the right, which would be positive infinity. That graph is increasing. If you have a change in direction, I'm getting ahead of myself, but it's just good to know it. If you have a change in direction, you have an extrema value. Does this problem have a minimum or a maximum, do you think?
It has a minimum.
A minimum. If you change direction, you always have an extrema. And again, like I said, extrema means a minimum or a maximum. We change directions, we'd call this a minimum. And since it's the lowest point on the entire graph, well, you'd call that an absolute minimum. That's an absolute minimum because it's the lowest point on the entire graph. So as you write that down, I'll just keep talking. Some graphs will have more than one minimums or more than one maximums. Anytime you change direction, you can get a maximum or minimum, but only one can be the absolute lowest. That's what absolute means. It's by the lowest point on the entire graph. All right, let's look at part B. This time we add a little twist to this. So starting from the left, remember we work to the right. What's happening at the beginning? Decreasing until this point. We're gonna have a change of direction right there. That point, if you were gonna label that, it looks like half unit left, half unit down. I would label that as -1/2, comma, -1/2. Now, the numbers are the same, but just as a matter of practice, do you label using the x values or the y values?
The exile.
X values. Okay, so we're coming from forever to the left. Let me write the word decreasing here. Sorry. Decreasing. We are decreasing from what x value represents forever to the left? Negative infinity. And we keep decreasing until what x value? -1/2 or -0.5. Both are correct. Then we switch directions, which means we now are increasing. We increase from this point to this point here, which looks like a half to the right, half up. So +1/2, +1/2. Okay, so where are we increasing from and then to? From the x value -1/2 to the x value +1/2. It's just a coincidence that the y's were the same, but you would be listing, technically speaking, the x values. I know that they're identical to the y values, but technically, if you want to be correct all the time, just note that you're going from x to x. Now I have this last portion. I have another change of direction. What's the last piece doing? It's decreasing again. So just like domain, I said that this is x values, but with parentheses always. Oh, I meant to say it's like domain. I meant to say x values, so parentheses right here, like domain. The only difference from domain is that it's always with parentheses. Sorry. Just realized I didn't fill that in. So it's x values, like the domain, but with parentheses always. Okay, so what does that mean? Since I have a second piece, I still follow the domain rules. If you have a second piece, remember how we did a union? That's what we do here. Union means we have another piece or the word or. So it's decreasing here or over here. So what x value do I start decreasing at? 1/2. And now here's what students will do wrong. Watch. They will put negative infinity. Tell me, why would we do that? Like, what would be the thinking? Because it does make sense. Because the y value goes down. It's tricky. But are we doing off the y values? No. What's the x value going to as you move right? Positive infinity. So positive infinity would be the correct answer there. Now, with those two examples, I want you to try one. DOL number 1 on the top of the next page. If you flip over, I want you to try this problem here. I'll give you a few moments to do DOL number 1. I will, the one thing I will throw off, this graph, the textbook could have came up with a better equation. They're going to use this point right here, which I'm going to call this point, though it's not the actual extrema, I will call that it's left 1 down 2. So, you know, -1, comma, -2. Okay, with that, now you try. So finally, the biggest point of this lesson is extrema. Let's talk about extrema. I kind of hit on it. An extrema is anywhere the graph changes direction. So maximum would be where you change from increasing to decreasing, creates a maximum. And if it's the highest point on the entire graph, you call it an absolute maximum. So on yours, I know this isn't the clearest image, but on this one, make sure you mark that as an absolute maximum. And I'm just going to say absolute max for the sake of time. Absolute max. This one here, you could call it one of two names. This lesson is going to use the word relative. Local is what most of our calculus teachers would say. So I want you to know it could be the word relative. It could also be the word local that you see, local maximum. What that means is it is a maximum, but it's not the highest point on the graph. And you can label these down here, but I want to change my graph just a little bit just to make sure we're fully understanding. And we're going to label that bottom portion since it doesn't give us the answers. Let's say the graph looked like this. So there's an arrow, there's an arrow. Tell me about this point right there. It's the lowest I see, but I have arrows. Would that make this a absolute or a local?
Local.
It would be a local. Why is it a local when it looks like it's the lowest point in the graph?
The arrows go down forever. So.
The arrows mean this graph actually goes lower and lower, but so that would make that a local minimum. Even though it appears in the image is the lowest point, it's not the lowest point in the graph. All right, you can label these if you want to. I'm just going to leave it like that. So now let's look at the problems. For example, 2. Here's our first graph. Be aware that this x-axis is counting by 2s. So if you want to write in, that's a 2. So it goes 2, 4, this would be 6 and 8. The y-axis, on the other hand, counts by 4s. 4, 8, 12, 16. Notice that's counting by 4. So it's a little bit tricky. On this graph, I see 2 extrema. A lot of students will wonder if it should be 3. It's actually only 2. I'll explain this one in a second. This extrema right there. Remember, we're counting by 2s. If this x value is -2, what x value you want to say this is if it's in between 0 and -2? How about -1? We'll say that's -1 as the x value, -1, and then it appears it's on the line of -8. So there's one extrema. We'll talk about what type it is in a moment. And then this one, I'm going to put this as if it were kind of in the middle of this line. Okay, what x value is this extrema on? 2. And let's say it's in between 12 and 16. What number is in the middle? Let's say it's at 14. All right, here's how you could write this. You could say, and I'm going to, since this is honors, I'm going to prepare you for calculus. Here's how you'd see it in calculus, is they would say, I'll do this one first. F, parentheses, that's because the equation's name is F. F -1 equals -8 is a, would you call this a local or absolute? Local. Again, the lesson will use the word relative, but your calculus teachers are going to say local. I'm sorry, did I say absolute? I meant to say relative. Your lesson will say relative. Your calculus teachers will say local. So I'm going to use their terminology. It's a local minimum. If you were trying to get credit on the AP exam, that's how your teachers would teach you to write that. F -1, that means the x value, the domain value is -1 equals -8. That refers to the y value, or the f, the function value, the range is -8, is a local minimum. All right, how would we write this one? F of which one? F of 2 equals 4, is a local max. Why is it not an absolute? That's right. The arrow off the side tells you that there is a higher point in this graph. Okay, now this middle thing right here, that is what you call a point of inflection. Point of inflection. We don't deal too much with that in pre-calculus, but that is what it's called. This is not a max nor a minimum because it doesn't change direction. Remember, a maximum minimum occurs, it'll look like a hill or a valley. They occur when you change direction. So this was decreasing, now it's increasing. Notice on this little, it does have a little flex in there. I'm going to call it flex as it says inflection. It has a little flex in there, but the truth is it's always increasing. Since it never changes direction, it's not an extrema. If that makes sense. That's how it works. Okay, and now your turn. I'll let you use this graph, and I would label these 2 points, that one and this one. I know they're not exact, but let's use those two. DOL number 2.
This time by one.
Yes, count it by ones. Great question. All right, example 3. Now let's use technology. I have not graphed this one. It's weird. I saved, when I went through this, your DOL problem. So I have your DOL problem back in that same Desmos we've been using all day, but I did not graph this one. So I'm going to type this one in real quick. F of x equals x to the 4th minus 5x squared minus 2x plus 4. Desmos is fantastic for doing Extrema because you don't have to analyze the graph or anything you had to do in the old Inspires. On this, you just click. I'm going to zoom in a little bit so that I can see these and make sure I'm clicking the right points. Desmos will show anything what's called a critical point, which means, like, for example, it'll show the y-intercepts, it'll show x-intercepts, or zeros, if you want to call them that. It'll show those points. But in this problem, I'm not interested in that. I'm interested in Extrema. So I want to make sure I only click the 3 Extrema. So I have 3 Extrema clicked here. And I read the problem. It says approximate, which just means round, to the nearest hundredth, the relative or absolute extrema of this graph. State the x values where they occur. Again, I'm going to write the answers in calculus form. So the first one, it says, before I do this, to the nearest hundredth. If you're not sure how rounding works with the English words, here's how I think about it. 100, the number, I know this is hundredth, but 100 looks like this. How many zeros do you see in the number 100? Since there's 2 zeros, it always goes off the zeros. 2 zeros means you're going to round to 2 decimal places. So if you're wondering, would that apply for all of them? Yes. If you were rounding to the nearest 10th, how many zeros are in 10? 1, so you'd round to 1 decimal place. If you had 1,000, how many zeros are in 1,000? 3. You'd round to 3 decimal places. That's how it works. So here we're gonna round to 2 decimal places. First one, the x is in good shape already. So we'll say f of negative 1.47 equals, all right, I got to round the y value. 0. I need it to be 2 decimal places. Does a 5, I think y'all learn in DISD, does it raise the score or does 5 let it rest? 5 or great more, raise the score. So that's going to be 0.81. 0.81. 5 or more, you round it up. 0.81 is now what is that point? Local or absolute minimum or maximum?
It's a local minimum.
Local minimum is a local minimum. And you could just write local min. Okay. What about this next one? Here, I need to round it. F of negative 0. Okay. Should it be 0.20 or 21? It's a 3.
0.20.
0.20. So I let it rest. Equals y value 4. Will it be 0.20 or 21? 20 is a, now what is this one? Local or absolute, maximum or minimum?
It's a local maximum.
Local maximum. Okay, and again, I'm using calculus terminology because ultimately writing it like this will help you in calculus because it helps you understand the math language. That's what I call it, the math language. All right, this last one. I'll have f of the x value is 1 point. Okay, will it be 0.67 or 68? Let it rest, 67. Or less, let it rest. And the y value, negative 0.50, negative 0.51. Negative 0.51 is a
Absolute minimum.
absolute minimum. I guess I shouldn't say a, I should change that to an un. Is an absolute minimum. And that would be your answer for this one. All right, with that, here's your problem. And like I said, you don't even have to type this into Desmos. All you need to do is turn on that next graph right there. If you turn that on, you should be able to get your answers. I'm going to zoom in, but I'm not going to click them for you. I'm going to let you click it. What I'm going to do here now is I'm going to close off guided practice number 3. I'm going to clear that, and I'll also press the home button for later. And now let's go on to example 4. So now let's just apply this in real world. Businesses, data analysis use maximums and minimums all the time. So the word you see in the real world is optimum or optimize. And so that's what word I'm going to underline here, optimize and optimum. That's how this is going to come into play. What that really means mathematically is a kind of a translation. English word we often in real world will say is optimize. What that means mathematically is the maximum, is really what that's going to usually mean. So here's the problem. It says advertisements for a new car claim that a tank of gas will take a driver and 3 passengers 360 miles. After researching on the internet, you find the function for miles per tank of gas for the car is given here, where X is the speed in miles per hour. So just to be clear, X is the speed. I like to underline when it tells me the variables. It doesn't tell me the Y, but Y is the distance. That's what it's referring to here. Y is going to be the distance. It didn't tell me that. Or f of X will be the distance, in other words. But X is the speed. What speed optimizes? That means we need to find the maximum. What speed optimizes the distance the car can travel on 1 tank of gas, and how far will that car travel at the optimum speed? So again, I don't have this one graphed, so I'm just going to get a new graph by pressing enter or blank. I'll type it in. It's f of X equals negative 0.25 X squared plus, I know it cuts off, it's 3.5X plus 240 on the next line. There's the 240.
It's negative 0.0.
Oh, negative 0.025. Thank you. There it is. Now I can't see anything right now because I'm too far zoomed in, so I'll zoom out. And now I'm going to tie in something. Now that I've got that, let me make it wider. I'm going to tie in something that we learned, I think it was last lesson, and it's on real worlds. We deal with the relative domain and relative range. You remember this? So can you, remember X is speed. Can you drive a car negative miles per hour? No. If Y is the distance, could your car travel a negative distance? No. So honestly, this graph should be cut off. I'm just going to type it in here. There's a way of making Desmos do this, and it's by using these weird squiggly brackets. This will restrict. I'm just going to say X has got to be positive. X has got to be positive, and the Y's also have to be positive, which I can't remember if I have to write Y equals or f of X. Nope, it's not that. Well, it's not that either. I'm just going to leave it like this for now. So we would not look at negative distance on this problem. We would not look at negative distance. So what that means is I'm only looking at the first quadrant. Optimum would be the maximum value. Okay, so you now interpret the problem for me. Now I've kind of set it to you. I want to see if you latched on and can refer it back. As I look at this maximum value, what is 70 referring to?
Speed.
Very good. How'd you know speed?
X is speed.
X is speed. So speed, the best speed to travel for this car is 70 miles per hour. So if you're driving and you get a speeding ticket driving 70, what you should tell the cops is it's the best speed for my miles per gallon. I'm helping the environment speeding here. That would be what you tell them. That's a joke, but okay. What is the 362.5 refer to? You listened well because they never told you. What is the 362.5? The y-axis? Distance. That's our distance. So here's how I would write this. At the optimum speed, I'll say at the optimum speed of 70 miles per hour, the car travels, and you could use the word optimum a second time. I'll say car travels the optimum distance, and it might be ridiculous to write twice, but I am, the optimum distance of 362.5 miles. 362.5 miles. So that would be my answer to this real world problem. Now this next one, it looks like a DOL. We're actually going to do this next one together. All right, so in this problem, it says a square with side lengths x, so like these little 4 squares, is cut from each corner of a rectangle with dimensions 8 by 12. The figure is then folded along to form an open box. So let me show you where it's folded. It's folded along basically this corner. And the black becomes the base of the box. These areas in between the black and the blue become the walls to form a volume of a box. That's the idea of this problem. So it says the figure is folded to form the open box as shown as in this diagram. Determine the length and width of the box that allow the maximum volume. And so this box was 12 inches. But what we do is we cut off an X amount here and an X amount here, which we don't know how much, but we just know it's an X. Mathematically speaking, if it was 12 and you lose this X and lose another X, how would you represent the new length in this black line? That would be 12 minus 2x. Good, because we lost 2 x's. Now the width, notice the same thing happens. It was 8 on this blue line. But now the black line is shorter. It lost an x and another x. Mathematically, what does that mean our width is? 8 minus 2x. Now what I'm going to do to help me out is I'm going to say this is W, and I'm going to say this is L. The height of the box is made up of this little area. What is the height of the box? X. And so to make room for it, I'll put it down here. I'm going to say h is x. Now, if you remember from your previous math courses, the formula for volume is length times width times height. So we can solve this problem by saying the volume will equal, and I'm going to substitute. The length is 12 minus 2x times the width, which is 8 minus 2x, times the height, which is just simply x. If we type that in the calculator, we should get a graph. We want to know the maximum volume. So what we're going to do is look for the maximum on the graph. So over to my problem. Don't need that one anymore. Let's graph this. This is v equals 12 minus 2x times 8 minus 2x times x. And I get this picture. I'm going to change the color so it's not all just black in there. I'm going to make it red. Okay. Now remind me on real world problems. This is real world. Can we have x in this problem refers to the height? Can we have a negative height? No. So I'm going to go ahead and eliminate the negative heights by just doing that squiggly. X has to be greater than 0. The height has to be greater than 0. It can't even have a height of 0. That would be the way we started. So it has to be greater than 0. Secondly, can we have a negative volume? No. So I don't think it'll let me do v has to be greater than 0, but if it would, that'd be nice. Let's see here. V has to be greater than 0. No, it won't work. Okay, but either way, now what we're looking at is at least have a positive height. But let me tell you, this problem actually does not continue on past this point here. The reason it doesn't is once the graph goes outside the first quadrant, the rest is not real. And you might be thinking, well, this part's positive, but I'll show you why it's not realistic. If you had a height of, let's just say this is 6 point, let me just say the height of 7. Where's 7? Right there. If you had a height of 7, what that would mean to have a height of 7 would mean that you'd have to cut out 7 inches here because height is your x. You'd have to have a height that's to have a height of 7 inches. It would mean you cut 7 inches this direction. But think about it. If you cut 7 inches this direction and 7 inches from this direction, the whole piece falls off. You see, it's no longer realistic. You couldn't cut even anything up to 4 inches. And here's why. If you cut 4 inches from the bottom and 4 inches from the top, that equals 8 and the whole side falls off. So this real world problem stops once it gets out of the first quadrant. The rest is bogus. So I'm just going to draw real quick on the graph since I can't make it go away. This part of the graph is bogus. Oh, I know how I could do it. Since it's only this portion till x of 4, I just say 4. There we go. Let me turn this around the way we normally see it. I'll just say the x, the height has to be somewhere between 0 and 4. There's our graph. So I'm looking at this maximum. That is my perfect height, because remember, x refers to the height. That's the perfect height that gives me the maximum volume. What's tricky is on the answer choices. They were really tricky and they put that as an answer choice. But that is incorrect. I want someone to walk through why would this be the incorrect answer choice for this particular problem? It helps if you read the problem. It says we need to find the length and width. What did I tell you X represents? That's the height. That's the volume. That was in place of Y is V for volume. That's height and volume. We're not supposed to find height and volume. We're supposed to find length and width. So how do you actually get your length here? You plug it in. So it'd be 12 minus 2 times 1.569. And the width would equal 8 minus 2 times 1.569. That's what X is. I'm going to let you do that to come up with your solution. So I'll give you a moment and then we'll continue on. Finally, let's now look at what's the back end of the lesson, average rate of change. So average rate of change, when we use this, means that we are dealing with a curved graph. A curved graph doesn't have a consistent slope. We're used to, from Algebra 1, lines that have a consistent slope. But when we get to graphs that are curved, the slope is changing. If you want to find what's called kind of like the average slope, the way to do so is you pick 2 points and say, okay, I will find the average slope between those 2 points. And you use, they give this formula, that's the calculus way of writing it. But the way you learned it in Algebra 1, which is still helpful, and I'm going to write it here, is that you take your second y value and you subtract the first y value divided by the second x value minus the first x value. That's how we found slope. Rise divided by run, or y2 minus y1 over x2 minus x1, where these 2 points you could rewrite as x1 comma, whoops, I forgot to write x1. Let me try this one more time. x1 comma y1, and then that's a comma. And then over here, this point would be x2 comma y2. If you did that little formula there, you could get what the average slope of the curved line is, which was represented by the red, what we call secant line. So a secant line is a flat line that cuts through a curve at 2 points. So we're going to work through 2 problems together here. I have an equation here that I'm going to go graph in Desmos because I think it's a lot easier if you look at the graph. So I'm dealing with the equation f of x equals, whoops, I mean to do capital, f of x equals negative 2x squared plus 4x plus 6. And I'm specifically going to be looking on the interval from -3 to 1. And to help myself out, I'm going to do a table here. So I hit the edit list up here, the settings that looks like a gear, and I'm going to hit this convert to table. And that's going to really help me out in this graph, because what it's going to do is I can look at the point -3. That's an interval, means x values, -3 and -1. I don't need any of these other points on there. I just need -3 and -1. And it puts up, there's that point for -3. There's the point for 1. On our picture, the picture is not as clear, but it's trying to show you this. There's the 2 points we're using. So if you wanted to label your packet, this point here, according to Desmos, is -3, -24. That's going to be the x1, y1, because it's the furthest to the left. This point right here will be the x2, y2, because it's the furthest to the right. Honestly, it doesn't matter as long as you stay consistent. You could switch the order of the points, but as long as you stay consistent with which one's 1 and which one's 2, you're fine. So to find the average rate of change, which we could call slope, that's why they use the letter M, of the secant line, the red would be the secant line. The slope of that would be the y2, which I'm going to say is 0, minus the y1, which happens to be -24, over the x2, -1, minus the x1, which was -3. This is how you find the slope. So let's do a little mental math here. If I'm minusing a negative number, that's the same thing as adding. So we have a positive 24, and same thing on the denominator. A -1 plus 3 is 2. So what is 24 divided by 2? 12. So the slope of the secant line, or you could say the average rate of change, would be 12. That means the rise is 12 units for every 1 unit of run. This red line would be going up 12 over 1. It's hard to see there, but over here you can see it a little bit better that it is really steep line, up 12 over 1. All right, let's try part B here. Same equation, but I've changed the interval. So the picture is going to change, but it's the same equation. So on Desmos, what's so nice about this is if you're doing this on your homework, all you have to do is change your table. We're now looking at the points 2 and 5. That's my interval, which interval means x's. So I'm looking at the points 2 and 5. The x value is 2 and 5. So now I'm going to label my graph here in the notes. 2 is the point 2, 6. That'll be our x1 first to the right. And this one, they didn't draw it very well, but it should intersect right at 5, is 5, negative 24. That's our second point. So my slope of the secant line, or the average rate of change, will be y2, negative 24, minus y1. That's going to be the rise over the run, which is 5 minus 2, x2 minus x1. Doing a little mental math. What is negative 24 minus x4?
Negative 30.
Negative 30. And then 5 minus 2? 3. When we reduce, negative 30 divided by 3?
Negative 10.
Negative 10. That means this will go down 10 units. For every 1 unit, it goes to the right. Rise over run is, their slope is negative 10. That'd be your average rate of change. All right, you have a DOL to try. I would suggest you use your graph over here. I've actually graphed this for you. All you have to do is turn on the graph. It's guided practice number 5. And then you can do edit settings, convert to table, and just type in the 2 points you're looking for over there to get your points to work with to find this equation out. DOL number 5. Oops. All right, let's take a look at numbers, example 6 now. It says find the average speed. So this is really just a application of what we've been doing. Here it says the formula for the distance traveled by falling objects on the moon is d of t equals 2.7 t squared, where d of t is the distance in feet and t is the time in seconds. Find and interpret the average speed of an object, time at the interval from 1 to 2 seconds. So what's weird is gravity is different when you're referring to stuff on the moon. And so let's see if it says feet. So on Earth, it falls at 16 feet per second squared. That's where that question, that amount comes from. And negative refers to it's falling down. What's weird in this one is it does not list it as being a negative value, which I think it should. But either way, this makes the object look like it's rising over time, which is falling. So honestly, it should be going that direction. And so I'm going to clear this one out so you can see this. And so we want to find out exactly how fast it's falling. And that's why, well, it's saying the average speed. So maybe since a speed can't be negative, typically we all use it this way, but I'm going to go to table here and we'll look at the values. We want to find after the falling between 1 and 2 seconds. So that's really what I want to see on my table, is just from 1 to 2 seconds. We want to find the secant line between these 2 points. This would be the average speed of falling. And so let's see here. The average speed of the object would be, you would use that same, the secant line formula. And so I'll take my second value of 10.8. That's the distance it fell, and or where its position is now, minus the original, which is 2.7. And on the time, you'd have 2 minus 1. So what this is going to say is for every 1 second that the object has moved, for every 1 second, it has moved roughly 8.1 feet. And so the average speed here is that the object, object is falling 8.1 feet. I don't know why I did rounding. This object is falling 8.1 feet per second between 1 and 2 seconds. That's the speed at which this object is falling. And so that would be part A. Now part B, we want to do the same thing, but now we want to look between 2 and 3 seconds. So now between 2 and 3 seconds, let's just use the same formula again. The object would fall 24.3 feet minus the original distance it fall on, which was 10.8 feet. And again, we'd have a final time of 3 seconds minus the original time of 2 seconds. And so here, when I do my subtraction, I think I'm going to have 13.5 in the numerator over 1. So this would say that the object is falling 13.5 feet per second between the interval 2 and 3 seconds on that interval. So with that, I'll let you try this DOL. All right, let's take a look at this ACP release question. It says a soccer player kicks a ball at an angle. The height of the ball in feet varies with time and is given by this function, where t is in time in seconds. What is the maximum height of the soccer ball to the nearest foot? So if you're thinking about this one, what we would do is just type it in. And once you look at your point, I have a question for you. How would you get your correct answer? If you see maximum, you would go to the maximum. And now what would be your correct answer when you look at that? It says, what is the maximum height? Which variable is height? The t or the h? Because h is in the place of y, you'd be looking at the y. And it says round to the nearest foot. Answer would be 17. And you need to bubble that in. You do not have to put the plus, but you do have to put the 1 and 7 bubbled in. And that would be your answer for that one. All right, let's look at one more ACP question. This is graphing piecewise. And so I started at the beginning of the lesson with this, and I'll finish here. If you go to your Desmos pre-programmed graphs and you click on the piecewise calculator, which is the second calculator here, and you open up this link, you could graph this equation and determine which graph is correct. So the first branch here, it says step 1, the first branch of this equation, which was just negative x minus 2, while x is less than or equal to negative 2. And so that would be this piece portion. The second piece of the graph is that we have a negative parentheses x squared, so it'll be upside down parabola, minus 4 between the x values of negative 2 and 3. And then finally, we'll have a third piece. So I'm going to open this one up. We'll have a third piece, which is just negative 6, as long as x is greater than 3. And so there's the third portion of the graph. Now, what's going to really help you with Desmos is it will show you a solid dot if there should be a solid dot. So when I look at this picture, I can quickly eliminate the top 2 graphs, A and C, because there's no gap between the second and third piece. There should be. And the Desmos tells me the bottom piece should have the solid dot. So B is the correct answer. Now, if you want to do this by algebra, this is telling you your range value given your domain. And I want you to see at when x is greater than or equal to 3, we have the point negative 6. So to walk you through it, here is 3. When x is equal to 3, it's going to equal negative 6 as a y. And so you notice that that's a negative 6. That's where that point came from. Whereas over here, the end of the second piece, it's less than 3, which is an open circle. And if you plugged in that 3 squared is 9, subtract 4, you get 5. Make it negative, we have a negative 5. Notice how this one's a 3, open circle, and negative 5 there on the y-axis. So that's how it works if you used algebra.